Oh, in the monastery, we analyze general relativity in the monastery. All right, since I ruined that, what's this? Don't pay attention to the little Stifu derivation there. I add that for a little hyperbolic effect there. But what the heck's a kappa? Well, you all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. Yes. So I was trying to put together a cool notebook and everything, and I still don't have my full Wolfram superpowers. We're working on it. Slowly but surely, I'm starting to pick up a few cantrips. We'll see what happens. But, alright, so what are we talking about? Alright, first, let's go over to our friend Wikipedia. Links are in the doobly-doo, of course. I actually labeled the last two. If you manage to scroll through like 2,000 characters, it's pretty easy with modern computers. Now, the Einstein Field Equations. These are the whole things with the Ricci tensor, the energy momentum tensor. You got all this stuff right here again. It's worth for Wikipedia. But the interesting thing is, it's one of the few places you actually find this. It's essentially the C4 convention for Einstein Kappa, sometimes referred to as the Einstein Gravitational Constant, defined as Kappa is equal to 8 pi times g, the Newton gravitational constant. We have another video, I forgot to link it, I apologize, divided by the speed of light raised to the fourth, and that comes out to be 2.076647442844 times 10 to the negative 43 newtons to the negative 1. What the heck is all that jazz there? Well, we're going to try to break this down. Actually, let's go to our friend Wolfram Alpha here. We're cheating a wee bit. There's just a hyperbolic vortex equation there. Okay. So what's a Newton? You're gonna want to be, oh no, we want the unit, not the person. There we go. All right, 1 Newton. What is this? All right. This I derive kilograms per times meters per second squared. All right. So as we can see, it's got dimensions mass, length, time raised to the negative 2. Cool. All right. So we've got that there. All right. Let's go to a little something else here, because we want to be fair and balanced as best we can. So this is from Physics Stack Exchange. Data about the constant Kappa of Einstein's field equation. I'm trying to understand each of these terms in the equation intuitively, but I'm having a little trouble. You can represent it as this. All right, we get our little tensors there and everything. So they're going back and forth, but essentially this nice person here kind of ends up deriving it. To the best of my knowledge, I assume they're a much smarter person than myself. So what are we going to do? So what we're going to do is we're going to apply the universal binomial factorization equation. Basically, it's the method that Thad derived to help basically describe the constants of nature to the best of our observational measurements here. But hey, welcome, Papa. Good to see you, my friend. All I know is the ancient Egyptians, they were some really smart folks. They built things that's like, nowadays, it's like, yeah, that's, they had a lot of labor. I think I'm allowed to say that. But all right, let's continue. So what we're going to do is we're going to set up the equation equal to that. All right, so that whole 8 pi g times c4. All right, there. And we're talking about the speed of light raised to the fourth, not the other one. All right, as we can see here, oh, my helps if I actually share my screen. There we go. Our friend Wolfram Alpha, like in the doobly-doo. All right, so if we take that, we get approximately 2.077 times 10 to the negative 43 seconds squared per kilogram meter. Yada, yada. So basically, it's an equivalent of joules as well. As you can see, oh, look, this. 1K, Einstein constant, the C4 convention. I think that's what we're talking about. That's cool. All right. So we got that, and it should have the dimensions. Yeah, mass -1, length -1, and then time squared. It's very interesting. Because if we go back, oh no, I just closed it. But the picture at the beginning, basically, Thad kind of wrote it out and he canceled out the little things and everything because gravity has similar units. So you end up having something like this. So you got 8 pi, then the Planck time, because as we saw, time squared, and mass -1, length -1. So mass -1. So basically, they're in the denominator there. See? Like time squared, blah, blah, blah. All right. We do that out. That comes out to be, does it give us more digits? No, not for this one. Okay. So basically, we got the first 4 significant digits there. That's cool. All right. So we go there and get our kappa. Nope. Too far ahead. Okay. So we take the number. And again, we're taking this from Wikipedia. Take it for what it's worth. So we take that number there. We plug it in over here. Okay. So we're using the universal binomial factorization equation. Hey, welcome, universe. Thank you for joining, my friend. Okay. Some of the screenshots at the beginning and everything help make this a lot more intuitive. It's also in the thumbnail. But, all right. So this is the magnitude of the Einstein gravitational constant. Since we're setting it equal using the boundary conditions, basically, what is it? Planck time squared divided by Planck length divided by times the Planck mass. So we got that here. So we set it equal to the magnitude since we're using those dimensions. So we have our, all right, our Planck time squared. Let's divide by the Planck length times the Planck mass. As we can see, we have those magnitudes there. And then we're multiplying that by 8 pi. It's basically 2 spheres or 4 circles, depending on one's interpretation. So we get close. So we get close to it. What was it? This is where I ran into the issue with the notebook here. And then, because the thing is, it doesn't hit it head on. Because the other one is, what was it? 2.77. Yeah, 2.77. We need 2.766. Yada, yada, yada. Okay, so that's why we have our terminal action. Because that had noticed right around about 7 significant digits, a lot of things kind of start to get wonky. I'm not saying that's one of the reasons past couple of years, back around 2019, when NIST redefined SI, they were trying to make it more coherent to line things up. It may have been a factor. Speculation. Okay, so the terminal action is 1 plus x, and then we multiply it by basically the Chinese symbol for field, basically for field theory. And that happens to be 10 to the -7. So actually, let's go over to our friend Noon. So that's, what was it? Planck mass, Planck length, and then that's all over the Planck charge squared. Carry, go. Oh, yeah. All right. And this is an interesting thing in and of itself. What's this? 1 times 10 to the -7. It's the magnitude of Ampere's constant. The Biot-Sievert constant. So that's a separate story. We'll get into that a little bit more deeply. I think there's some previous videos on there. The interesting thing, you got mass, length, you get charge squared. When you get up with the dimensions, mass, length, time -2, and current. Because charge happens to have a something to do with time. How very interesting. That's just a side note. Okay, so we go back over to our equation here. Okay, so we got the Einstein kappa. That's the magnitude. We just plug the number into Wolfram alpha. We have a primary action, which is 8 pi, so basically 2 spheres. And then we have our boundary conditions, Planck times squared, Planck length, and then times the Planck mass. We're dividing that all right there. Okay. We have that number there, that 1 plus the x. And then we have that magnitude of 10 to the negative 7. Okay. As you can see, I was copying the stuff, trying to put it in the notebook to get it to work, but I'm just like, I didn't feel like spending hours to try to figure that out. I'm like, I already know how to do this. So, okay. So we get our x. What happens when we search for this x? So now we basically do the same thing. We're like, what can we multiply this by to get to that, whether we need a squared or whatnot? And that's where our friend the hyperbolic vortex equation comes in. This is, and the claim is, the hyperbolic vortex equation. When you have a lambda, basically, when you subtract out this magnitude, which happens to be the Planck mass, it solves for the fine structure constant, or quote unquote, colloquially, the true fine structure constant, as Professor Feynman may say. So we got our 1 over x plus x cubed divided by 2 pi, set equal to I raised to the I raised to the negative pi divided by 2 minus the Planck mass. Okay. Again, there's other videos and stuff on that. But basically, we get these 4 answers here. When we square this one, let's just go into a new link. Boom. Square it. Okay. Let's take this. I don't know. Let's just take these amount of digits. Oh, actually, no. Let's just do this. Boom. Fine. Structure. Constant. Again, another sidetrack. I apologize. Okay. 0.729735257. Cool. All right. 0.007297352572958, and it just keeps going. Okay. Appears to be a geometric derivation of the fine structure constant. That's cool. Okay, but that's not what we're here for. We're here for, because we have these other answers. So what you can do is, in order to solve for our friend over here, which is the negative 52, yada, 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 in order to find a geometric action that can help close this, what we do is, basically you literally just go through, you set that equal to like we had it over there, and then you'll take this, and then you solve for x. And then you square it, and then you do it. And you basically just keep on searching the computational universe. That's one of the reasons I wanted to develop Wolfram Superpowers, so we could basically make a packlet to just basically do this without having to do it by hand. Don't get me wrong, it's basically like treasure hunting, and there's some pretty cool treasures, I claim. And I'm going to give my opinion on the interpretation. So this one, I'm not going to go through the whole dang thing there, because I literally spent hours looking for this. I showed it that. I found a cool answer. The answer that was kind of cool, it got like 7 or 8 significant digits. This one more or less nailed it head on. I think it's off by a little bit for the very, very end there. I think it's like 12 significant digits. But this, we happen to use Je2. Again, Je1, Je2, Je3, Je4. I get these in different. That gets this one first for some reason. Again, everybody's internet happens to be a little bit different. This is one of the things I've learned over time. All right. So the best answer that we found to fit it is Je2. So we'll go back over here. So this is Je2. We just got that number there. So we had our first number. That was our x. That's when we plugged in that whole big long thing here. It gives us this negative 52.97867. All right. So the answer I happened to find, well, I was at the monastery. We take Je2 and we raise it to the 5th. And we multiply by x. Okay. So it gives us this number here. What happens when we go to this number here? You literally just search Wolfram Alpha for this number. And you're looking for a potential closed form of this. Something that makes sense. Like, so if you see like 2 pi, I don't know, lemniscate constant, the thing that makes the infinity sign or the figure 8. Basically, you're looking for a geometric action that might help us to interpret what's going on. So when we go through and we look for possible closed forms, okay, kind of interesting here. Oh, what's this? This one nails it head on. This is negative 5 CET. What the heck is that thing? That's divided by 44. That's the name of Thad's book, 44. 44 derangements in the shape of persistence. Oh, very interesting. That basically comes from when you take, let's go back here. So basically the derangements of 5, which happens to be the number of dimensional flavors or ingredients, as some may say, to create our realm of persistence, what we colloquially refer to as our universe. Time, space, charge, mass, and temperature. You might get a fancy thing like for the Boltzmann constant, but those 5 ingredients basically can help create the constants of physics as we know it. That's pretty neat. All right. So you do that. So basically, that's the number of permutations. Yeah, so exclamation point 5 is the number of ways you can rearrange 5 different things. Happens to be 44. That's cool. So, and it hits it for all the significant digits. That's kind of cool. So, CET, since it's Wolfram alpha, CET is the Embry-Treffelin constant. Hey, Moira, thank you for joining. We're just trying to figure out the Einsteinian gravitational constant. So cats are very important. Meow. Okay. So what the heck is that constant? So when you click on this is very interesting. Go to the definition from Math World. It's not the M. That's not the M. What the heck is it called again? The Embry-Treffelin constant. Butchering that, I apologize. But it leads us to the random Fibonacci sequence. Papa's going to like this one. But basically, the Fibonacci numbers, those are those things where you can help be like, oh, well, you're doing this, you're doing that. Basically, seems to be a very strong connection with the primes. It's very interesting. A random Fibonacci sequence. What the heck is this? Consider the Fibonacci sequence like recurrence. A of n is equal to plus or minus A of n minus 1 plus or minus A and n minus 2, yada, yada, yada. So you keep on going. So where A of 0 equals 0, A of 1 equals 1, yada, yada. Each sign is chosen independently and at random with probability 1/2. They showed that basically as the limit goes to basically that, 1.13198824, yada, yada. With probability 1, the constant is sometimes known as this Wannath's constant, considering the more general reoccurrence. So basically, you just keep on going through, okay? You see the limit there. Okay, that limit to infinity exists for almost all values of B. The critical value of B star, such as that the sigma of B star is 1, given by B of 0.70258. What? Why are there only 5 significant digits? What's going on here? Most of these things, we have lots of them. So, and that number there is sometimes known as the Embry-Treffelin constant. Basically, that's that CET thingy right there within the Wolfram language there. Hey, welcome, Max. Good to see you. Wolfram Alpha it's one of the greatest tools in the frickin'. There's a reason they're connecting ChatGPT to it and everything for select users. But I'm working on my certification. I'm literally starting it now so I can do this because I've listened to a lot of the different lectures and stuff like that. I'll hear it, but it's like when it comes to actually doing it, it's like I haven't actually done just going through the course and just literally just typing in the things as you're going through. I'm slowly picking. I view it as wizardry. You got to practice because even Professor Wolfram's like, Yeah, there's a learning curve. You need to get over that hump. Once you get over that hump, you can do most everything. It just basically comes down to searching and knowing what you can do. Working on my wizarding skills. Hopefully I can learn, what's that spell again? We'll see. Since Fibonacci numbers can be computed as products of Fibonacci Q matrices, this same concept arises in the iterative multiplication of pairs of 2 by 2 random matrices. Oh, that's cool. But when you go to this thing over here, okay, the online encyclopedia of integer sequences, decimal expansion of the Embry-Trefethen constant, 0, 7, 0, 2, 5, 8. There are literally only 5 significant digits. When you look into the history of this, it's apparently an incredibly hard thing to do, and to get that far was using modern computers. Huh. Imagine just a sequence where you're basically just flipping the convention minus or plus. Just such a simple thing from such simple rules as this. You can get such amazing complexity that we really can't even calculate it there. Like the amount of computing power is ridiculous. Okay. So let's go back over here. Go back over to our friend. Okay. So why does this stand out? Okay. Number 1 is number 5. Within Thad's model, the mineral arena, or what I like to refer to colloquially from Jen as the HF8 model, the hyperbolic figure 8 knot model. N is 5, basically the 5-dimensional flavors of reality: time, space, charge, mass, and temperature. We got 5 of those things. We got CET. Huh. So if I'm going to be like, it's something with a random Fibonacci sequence. Well, Professor Einstein basically once said, God does not play dice. Hypothetically conjecture, God doesn't play dice. What's the closest that God could, or at least whatever entity, whatever realm, whatever you're going to consider, get the closest to random with the most simple things as possible? I don't know, maybe a random Fibonacci sequence? It's a very beautiful thing. It's very simple. You're just doing that plus or minus, plus or minus, plus or minus. Huh. And with modern computing, we only know 5 significant digits. I claim we live in best universe. But, okay. So let's plug it in. Oh, yeah, the last part. Yeah, 44. So that's basically the explanation. That's the number of permutations of 5. So it's pretty. It's pretty. It lines up with the model. But does it hit the data? Well, that's the important thing. So you have all the things you want, but if it doesn't connect with experiment or what we observe in the real world, well, that's the point. All right. Here's the point. So as we can see, we put our crazy equation in here. All that is what we had before, except we don't set it equal to. We see how close we can get. So we got our 8 pi, basically our 2 spheres there, times our boundary conditions, Planck times squared, divided by the Planck length times the Planck mass. Okay. And we have our terminal action. This is the 1. And then, basically, we have our Je2. This is Je2. It's the second answer to the hyperbolic vortex equation. Our Je2, and that's raised to the 5th, which is also very interesting. Just saying. And we multiply that by the answer that we got over there, which is the closed form of this, at negative 0.0798381. Okay. Plug that in there, and that's multiplied by that 10 to the negative 7. Cool. All right, so it divides it because it's that. We get this monstrous number right here. 2.0, yada, yada. Okay. So we go back to our friend Wikipedia. Number we're looking for. Let's make them next to each other. Oh my God, I swear I can do this. Okay. Number we're looking for is 2.07. 2.07. 664. 664. 474. 474. 428. 428. 44. 28. 4. Oh, 9. Oh, he's off. I apologize. We only got the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We only got the 12 significant digits. I'm gonna make a claim. I claim this, my friends, appears to be a geometric derivation of the Einstein Gravitational Constant Kappa. I know, we're out there, but hey, Jeremy, thank you for joining. No, it's hey, Talisman started as a stone. It's totally fine. Long game, my friend, long game. So, yep, that's what we have right here. So I feel comfortable sharing that just because I actually searched for that. Like that's one of the reasons I'm almost a little proud of myself. It's like I actually found these things. Could that have done that? Absolutely. He developed the whole method, but it's like, yeah, if you got one dude, and I'm gonna be talking about a dude and be like, I think this guy is onto something that's very worthwhile. Hey, I remember a wise man once said, don't sing it, just bring it. And that's why I actually have to do the stuff myself, because it's like, why would anyone else do something if you're not willing to do it yourself? So that's what we're here doing. But that's all we got for right now. Peace out, guys. Take care of yourselves. It's a wacky and wild world out there, my friends. But all I know is occasionally a hat may help.
We won't be going hungry if we do this. That's for sure.
Dude, my hat has made over $10 tonight.
I guess I'm going to have to wear a cowboy hat on here with you next time, too.
Howdy.
Peace out, everybody.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.